During its long history, the Earth has seen radical changes that altered the destiny of life on the planet. How can we look into the past to discover how living things reacted to these changes? Scientists are tapping deep into the seafloor, the land, and ice to discover fossilized remains of microscopic creatures that reveal the chemistry of the oceans long ago. Join us now for a conversation with paleobiologist Brian Huber to learn how small life forms can tell big stories about climate change on Earth millions of years ago and today. Now, here's your host, Maggie Benson.
Welcome. Thanks for joining us for another episode of Live from Curious, Smithsonian Science How. I'm Maggie Benson. We're really excited to have you here today and thrilled to have with us paleobiologist from the Smithsonian's National Museum of Natural History, Dr. Brian Huber. Thanks for joining us, Brian.
It's great to be here.
Let's start off with learning what a paleobiologist is and what you do as one.
A paleobiologist studies evidence of past life, like fossils, and we try to understand the environments in which those fossils occur. So we study sediments and then the shapes and sizes and locations of fossils.
Interesting. So I know that you focus your research on tiny organisms called foraminifera.
Yeah.
There has to be an easier word for that.
Well, the nickname for foraminifera is forams, and these are microscopic organisms that are protistans, single-celled, and they secrete a shell. And the shell is what forms the fossil record of these organisms. You've got two kinds. One's called the benthic foraminifera, and they live in the top few centimeters of the ocean floor. And these have a fossil record that goes back 540 million years. Planktic foraminifera, shown on the screen, have a fossil record that goes back 180 million years ago. They float in the upper 200 meters of the ocean. They're found together in the ancient sediments, and so by studying these things, we can reconstruct the ocean bottom environments and the ocean surface environments.
So you mentioned that they're found in these sediments. Where are these sediments found, and how do you collect them?
Well, ocean sediments have foraminifera worldwide in the deep sea, but also in the geologic past, we've had oceans that flooded the continents because of much higher sea level. So you can actually find foraminifera in chalk in Kansas, in Colorado, in Montana, because the oceans flooded the continents all the way across North America during the geologic past. And so by studying these sediments worldwide, from the Arctic to the Antarctic to the tropics, you can reconstruct Earth history.
So if I find some marine sediment, can I just get a handful of it and have forams, or how do I get them out?
Well, forams, fortunately, because they're tiny, a lot of them are less than a millimeter, even less than half a millimeter in size. Many specimens occur in a small amount of sediment. When you go to marine sediment, you can get something like chalk, and you just put it in water, and it'll disperse in water if there's not a lot of cement. Then you wash that through a sieve, and that screen contains the sand-sized material that concentrates the foraminifera. You dry that material, you pour it into a tray, and then you can then put it in a vial, and you label the vial with a sample number. And then you can use a dissecting needle or a picking brush to move the specimens around under a light microscope and then put them on a little microscopic slide for study and identification.
Interesting. So what are forams used to tell scientists about? As a paleobiologist, they must tell you something about life in the past.
Well, benthic foraminifera have different distributions with depth in all kinds of environments, like oxygen content of the ocean during the past. Planktic foraminifera tell you about the water environment, but both of them in their shells have a chemistry that allows you to reconstruct past temperatures.
And so do different forams occupy different temperature ranges in the ocean?
Yeah, so some species occur only in the tropics. Other species only occur near the poles. And so the modern distribution tells us that planktic foraminifera are very temperature sensitive. And this is the case during the geologic past. You have restricted distributions that can tell you sort of where the climatic belts were located.
So forams are trapping temperature information in their tiny shells, but are they also telling you how old they are so that scientists can know how warm it was in the past? When?
Well, like any fossil, there's a time when that fossil species first appears in the geologic record and then a time when it goes extinct. Planktic foraminifera are especially useful for telling geologic time because some of their age ranges are really short. Some species only exist for about 1 million years, others maybe 15 million years.
Is that what we're looking at right now?
Yeah, if you measure any sequence of rock, you can go up through time, basically, from the oldest sediments, in this case, in the section that was measured at the bottom, and you'll see that at some point, a species goes extinct. Other species appear, sometimes they overlap. By comparing these assemblages, then you can reconstruct the kind of environment, or kind of geologic time, and narrow it down based on studies worldwide.
Now, you just said that 1 million years is a short interval of time. 1 million years seems like a long time to me.
Yeah, in human time scales, it's incredible to imagine 1 million years, let alone 100 million years. Remember that the Earth is about 4.6 billion years, so 4,600 million years. So forams, with their record back to 540 million years, are a pretty small part of that whole Earth history. 1 million years is like next to nothing.
So you've told us a little bit about forams and how they're used to understand Earth's temperature at a specific time throughout the foram history, at least. But I'm really curious what this kind of information tells scientists. What do you say we ask our viewers?
Yeah.
All right, viewers, now's your chance to tell us what you think. You can respond to this poll question using the window that appears to the right of your video screen. Tell us, what do forams tell scientists about? Global climate change, evolutionary change, extinction events, or environmental conditions? Take a moment to think about it and put your answer in the window to the right. And remember that this is the same place that you can post questions for Dr. Brian Huber to answer during our live broadcast today. Brian, the results are still coming in, but the majority, 71% of our viewers, think that forams are telling scientists about extinction events. What do you think?
They do tell about extinction events, but they also tell about the other things that were listed. So forams are very useful for all kinds of information about the geologic past, climate change, and so forth.
So extinction events, our viewers must be interested in them. Have you ever recognized an extinction event in the foram record?
Yeah, actually, this is something I studied quite a bit for the earlier part of my career here. And the really fantastic thing about planktic forams is they're so sensitive to these kind of changes. And 66 million years ago, there was an asteroid impact that ended the dinosaur era. And this is something that everybody knows about.
And there's global evidence of that?
Yeah, this section is from Spain, and actually I took that photograph of the boundary between the Cretaceous age, when the dinosaurs existed in the Paleogene, after the extinction of dinosaurs. The planktic foraminifera in that section suffered 90% extinction across that interval. Now remember, this is a chalk sequence on land, but we also have records from the deep ocean worldwide, even both from pole to pole, that demonstrates this abrupt extinction event.
Do you have an example of that with us today?
I do. This is a deep sea core that came from off of northern Florida. And at the bottom of the core is a sequence that has the Cretaceous age foraminifera. And these are completely different from the forams from just above the dark layer in that core.
What part's the bottom?
Down here.
Okay.
So this is the Cretaceous age. And then this dark layer itself is full of little glassy balls called tektites. And that's material that was ejected from the impact bed. And this ejected material shot through the atmosphere and then fell from the sky and was deposited in the ocean bottom. At the top of that impact bed is a rusty colored layer, which is the metal of the asteroid itself. And that fine dust was the last to fall to the seafloor. And just above that are the sediments where tiny species, the few species that survived, can be found. So completely different assemblages.
How can you tell that they're different assemblages? Do they look different, the ones before the asteroid impact and the ones after?
Yeah, they're really different. Size-wise, the ones before are quite a bit bigger.
Like the ones we're looking at now?
Yeah, you can see the shells are quite different sizes. Some of those shells are very ornate, very pretty little keels. But there's a diversity there that's on the order of maybe 30 species. But when you go above this extinction level, you have very few species, and they're much smaller. So only about 2 species survive this event. And then very quickly you see evolution of new species right within a few millimeters after the impact bed.
Wow, that's fascinating. Now, you must have a collection of forams here at the Smithsonian's National Museum of Natural History to be able to really understand that those assemblages before and after the impact are different.
Yeah, my job is called curator. I oversee the largest collection of foraminifera in the world. We have hundreds of thousands of slides that are in our collection, and these slides go back to the 1800s even. And we have people coming worldwide to study these collections because we want to be sure we identify the species correct. And so we have the original vouchers with identifications for the species that were first named.
Very cool. Well, thanks for helping us better understand what forams are and how they help paleobiologists better understand life in the past.
Yeah.
So I know that early in your career, you studied in Antarctica. Why there?
Well, really it was luck. I got invited to join an expedition to Antarctica to see if there were foraminifera in a section of a place called Seymour Island. It's on the Antarctic Peninsula at 65 degrees south. And this island is not ice covered year-round, so it exposed sediments between 70 and 50 million years old. And so by mapping that sequence, then we could figure out what the ages of the sediments were. But the discovery that we made was that there was a very abrupt transition in the fossils there. In particular, we found that these things called ammonites, which are a type of cephalopod shown here.
Right, this one right here?
Yeah, so this is an ammonite. It's related to the nautilus, which survives today, but it's an extinct relative. These and things like this snail called Amberlea and a bunch of other things went extinct very abruptly right across the island. You can map the level where these go extinct. They also went extinct at the same level where mosasaurs and plesiosaurs, which are swimming reptiles, went extinct. So we knew we had an extinction level. It was from the study of the planktic foraminifera that we knew this was the Cretaceous-Paleogene boundary extinction event.
Interesting. And I see something else large on this table that looks like wood. Is this from Antarctica?
It is. And one of the things that left a lasting impression on me was working in Antarctica and freezing my fingers and my face. And then seeing this evidence of warmer climate, and particularly wood. We know that there were forests near this place where the marine sediments were deposited because this wood was deposited with the marine sediments. We found fossil leaves along with the wood deposited in the marine sediments. So all this stuff washed off rivers and into this place where we were finding our marine fossils.
Wow, I'm super fascinated to know that there were trees, there were plants, and reptiles in Antarctica, when we know now it's totally covered in ice.
Yeah, it's amazing. Today, the only thing that grows there is moss, which blooms once a year maybe, and lichens on rocks. No animals live there year-round, so obviously this is an environment that changed dramatically.
I wonder why Antarctica was so warm, and maybe we should ask our viewers. What do you think?
Yeah.
All right. Viewers, here's another opportunity to participate in a live poll. Tell us, why were these species in Antarctica? They drifted there on icebergs. These organisms used to be more cold tolerant. It used to be warmer in Antarctica, or Antarctica used to be in the tropics. Take a moment to think about it and put your answer in the window that appears to the right of your video screen. Brian, the results are still coming in, but so far 81% of our viewers think the answer is C, that it used to be warmer in Antarctica. What did your foram research tell you?
Well, actually, yeah, just finding the fossils themselves clearly showed that it was warmer at that time. But we could study the shells of the foraminifera, measure the chemistry of those shells, and determine what the water temperature was. And what we found was the planktic foraminifera living in the surface of the ocean were on the order of 10 to 12 degrees centigrade at this time, 66 to 70 million years ago.
And how warm is it there today?
Today it's freezing. I mean, we have ice, sea ice that covers Antarctica. So, we've dropped considerably since that time in terms of temperature.
So I see a key here. It's Cretaceous warm house. Is that the period that they call this time of warming in Antarctica?
Yeah, this was a time where there was actually no ice in any of Antarctica and no ice also in the North Pole. So we know that both poles were warm, and in fact, the whole Earth was warm. And so this Cretaceous age we call a warm house.
Interesting. So we have a video question for you. Are you ready to take it?
Sure.
All right, let's see.
Hi, my name is Austin. I'm from Dutchridge Elementary, and I would like to know from Dr. Huber if forams had a predator and prey relationship. Thank you.
Austin, that's a great question. Yeah, in fact, the major prey of forams today is fish. Fish will just suck in the plankton, and then they'll use their gills to filter out the plankton, and so that's their lunch.
Great question. So we have another question here. This one comes from Patricio, Indian Atlantic Elementary. What type of fossil is the most common that you discovered in Antarctica?
Very good question, Patricio. On the surface of these sediments in the Cretaceous age, these ammonites actually were scattered quite continuously throughout the sequence. But the most common thing, weirdly enough, is a strange calcareous worm. It's a worm tube with a calcareous or limey shell. And these things were like pavements in some parts of that sequence.
Great question. So this question comes from Wolfgang and Jonah. Are underwater fossils related to underwater animals we find today?
Wolfgang and Jonah, yes, indeed. We have a lot of living relatives of the fossils that we find. But remember, we're dealing with something in Seymour Island, for example, that's as much as 70 million years old. And so there's really no species that exist today that have such an ancient fossil record. But we have similar kinds of organisms in terms of we know whether there's a snail or whether there's a clam or whether it's a nautilus.
So I'm seeing pictures of extinct marine reptiles here. Do we have anything like that today?
All of those things in that illustration are extinct. That's a mosasaur, and that mosasaur is feeding on ammonites. All of those were victims of the asteroid impact.
All right, we have another video question. You ready to take it?
Oh, yeah.
All right.
Hi, my name is JJ from Dutchridge Elementary School, and I would like to ask Dr. Huber how scientists found the KT boundary line.
So how did we find the KT boundary line?
Yes.
Well, it's a very distinct change, and in fact, the color change as well as the composition and texture of the sediment in a lot of places changes abruptly because it turns right after the impact. There's a clay layer which marks the impact layer. So in the photograph shown, there's a line that I drew on that photograph, which is a distinct clay layer where the impact fallout is preserved.
And that KT boundary line, that's basically another way to say the impact bed where there's evidence of that asteroid impact.
Yeah, that is a distinct mark of a very brief, what we call bad day in her Earth history.
Absolutely. So we have another question, and this one comes from the students watching in the Curious Lab here at the Smithsonian.
All right.
And they want to know why forams go extinct so often.
It's a great question, actually, because throughout geologic history, species appear, they evolve, and they go extinct. Oftentimes, we try to find a mechanism to explain those extinctions, but many times we're completely mystified as to why they went extinct. You have competition between organisms, but also you have environmental change. So whether it's climate change or change in the chemistry of the ocean, there's many factors that could contribute to the extinction of organisms. Sometimes we just don't have the information in the geologic record to tease apart the story that actually would tell you that answer.
Great. Great questions. So Brian, I know that you did Antarctica research in Antarctica early in your career, but you also did research on deep sea drilling. ships. Can you tell us about that?
Yeah, the deep sea drilling ship is actually out there for science to drill ocean cores in the ocean floor. And so you can drill down deeper and deeper and get an older and older record of climate change, environmental change of the ocean. And in these sediments, foraminifera are often extremely abundant. And so those things are the storytellers. You can tease apart those sediments, analyze the foraminifera, and then better understand what happened in the past.
And what we were looking at before from the KT boundary is actually a core. This is what's extracted from those ships?
Yes, in fact, I was on the drilling ship when this particular core was drilled. This is from off of northern Florida, as I mentioned. It was drilled in 2,200 meters water depth, and then the core itself came from about 130 meters below the seafloor. Now, we knew what age this was by knowing the foraminifera in the sediments from the core, so we could anticipate how soon the core would come up when the Cretaceous-Paleogene boundary was drilled.
So you were deeping into deeper sediments on the deep sea drilling ship. Did you find any different evidence than you found in Antarctica?
The extinction story is the same worldwide. So we have many deep sea drill sites that show this impact bed. The impact bed gets smaller the further away you get from the crater where the impact occurred. But that's a global story.
And did you find any evidence in your research there that the Earth was warmer?
Well, the other thing that you can do with the ocean drilling ship, of course, is look for sediments of different ages. And the further back time you go in the Cretaceous, we find from the analysis of the chemistry of foram shells that we had an even warmer Earth than during the time of the asteroid impact. The graph that's on the screen shows a temperature curve that was put together from analysis of the shell's chemistry using benthic foraminifera from the deep ocean, probably greater than 1,000 meters water depth. And you can see from the present day we have freezing temperatures, but you go back in time, you see lots of wiggles. There's times where it was warmer and times that it got cooler. Go back further time, you look at 55 million years ago, it was very warm. There was no ice in either pole. But then you keep going back in time and you look between about 94 to 89 million years ago, and we have extremely warm temperatures, some reaching up to 20 degrees centigrade. And this time is called the Cretaceous hothouse, the Cretaceous hot greenhouse, whatever you want to say. This was an Earth which was extremely warm.
So even warmer than the conditions that you found in Antarctica.
Yeah, and the deep sea today at 1,000 meters water depth, water temperature is about 1 degree centigrade. So to have 20 degrees centigrade in the deep, deep ocean is amazing. We also know by drilling near Antarctica that the polar regions were extremely warm.
So on that graph, it showed a shaded box, and I understand that's where you're trying to fill gaps in the climate record. And you traveled to do some of your research in Tanzania. Were you looking to fill gaps in that record there?
Right. We were looking to fill gaps in the age interval that was missing for the putting together this record, but also because Tanzania was in tropical latitudes, we wanted to understand what were temperatures like that were near the tropics. And there's very few places where you can get good preservation to do this. But Tanzania sediments that used to be under the ocean bottom yield beautifully preserved foraminifera. And by analyzing those shells, we could reconstruct the temperature history through quite a long time interval.
We see that you collected cores from the marine sediment on land there. So what did the data that you found in Tanzania tell you about warming on Earth?
Well, we couldn't have had it better. Our prediction was that based on the climate models, if this is a CO2 greenhouse Earth, the tropics should also be warmer than present day. And sure enough, these really well-preserved foraminifera showed that the tropical regions in Tanzania were much warmer than today, on the order of 34, 35 degrees centigrade. Present-day tropics typically are about 28 degrees centigrade.
So it was very warm, and you mentioned that's because of rich CO2. How is the CO2 contributing to a warmer atmosphere?
CO2 and methane are types of greenhouse gases, and those greenhouse gases sort of form a blanket around the world atmosphere, and they trap heat energy so that it doesn't escape outside our atmosphere. And so the more CO2 and methane you have, the more greenhouse warming you're going to have.
And I just saw a map of the world from 94 million years ago with the increased amount of CO2 in the atmosphere in the way the world and the continents were arranged then. Did that have something to do with the Earth heating up?
Yeah, if you look at this map, you'll see that Australia's up against Antarctica. The Atlantic was much smaller. And there was a seaway going through the North American continent as well as all through Western Europe. So these factors contributed to the warming. The fact that sea level was much higher also tells us that we had much faster seafloor spreading as a result of the kind of continental drift that occurred. This caused much greater volcanism in the deep ocean floor. And so these submarine volcanoes pumped out a lot more CO2 because of the faster spreading rates during this time.
So it was much warmer 90 so million years ago. But today I know that the poles are covered in ice. I mean, Antarctica, your original study site, is ice covered today.
That's right. Well, one of the things that's happened in the last couple of decades is a huge loss of the shelf ice near Antarctica. And in one case, the Larsen ice shelf that was just shown in the photograph there broke up very abruptly, and a size of ice shelf, the size of Rhode Island, floated away and melted. And this is happening in Greenland, where there's deglaciation from melting of the base of the ice shelf. And also in Antarctica, the ice is moving faster. So we have a lot of loss of ice in the polar regions.
So it's really global evidence of warming after the poles glaciated.
That's right. In the Arctic, we know that the Arctic sea ice is shrinking. We also see from alpine glaciers, like Mount Kilimanjaro, the amount of ice is shrinking. And this is a global phenomenon. It's happening quite fast, very abruptly.
So what's in store for our future?
Well, when you consider that this ice that's been trapped on land for tens of thousands, hundreds of thousands of years is going to the sea, we know sea level is rising. And the prediction is we may have several meters of sea level rise in the next century or so. So cities that are near sea level, within a couple meters, are going to be flooded.
So the projection that we're seeing here, is that the melting of the Arctic?
Yeah, this is based on the prediction for climate warming over the next century. And based on that, we know that the ocean temperature warms, that's going to melt the sea ice, and what's going to happen is within a century we'll have shipping lanes going from the Atlantic Ocean to the Pacific Ocean through the Arctic. And you know, considering how frozen that is today, it's very hard to imagine this happening within just a century.
So whatever warming does occur, is that going to be trapped in the foram record?
Forams are great archives for climate change, and so we know that forams that were living in the last century, and then forams living today, and then forams living in the next centuries are going to record this whole transition from the pre-greenhouse world to the greenhouse world as a result of all the greenhouse warming from CO2 resulting from the industrial age.
Wow. So thank you so much, Brian. We're actually all out of time, but thank you for helping us better understand forams and how they are nature's natural data loggers.
Forams are really cool. I'm really glad to have talked about it.
Wonderful. And can you tell our viewers now where they can learn a little bit more about your work?
Well, I'm in the Department of Paleobiology at the Natural History Museum, Smithsonian, and we have a website that has links to story about the blast from the past, about the Cretaceous-Paleogene boundary. There's a link to what forams are, and there's links to lots of other fun stories about fossils and geologic time.
Awesome. Thank you so much, Brian. Thank you so much for joining us. The archive will be available later this evening on curious.si.edu. See you next time on Smithsonian Science How.
Thanks for watching. You can explore more Smithsonian Science How shows on our website, curious.si.edu. We hope you'll join us again on Thursday, March 12th, for a conversation with geologist Cara Santelli, where we'll explore the role that microbes play in the mineral cycle and their practical applications to pollution cleanup. Register now at curious.si.edu.